What if the universe is not what you think it is? Not a grand, cold void speckled with stars, not an infinite playground of matter and energy dancing to the tune of gravity. What if, instead, it's something quieter, something deeper, colder, and far more calculating? Imagine a reality that does not arise by accident, but by process. Not a simulation, not exactly, but something even more real, a computation, a quantum computation. For nearly 14 billion years, this process has unfolded. Every particle interaction, every twist of time, every flash of light, every breath you take, all may be the steps of an algorithm, advancing tick by tick, moment by moment, not because someone programmed it, but because that is what reality does. Some physicists believe this to be more than theory. To them, the universe is a machine, not mechanical but logical, not gears and pistons, but logic gates and probabilities. A quantum computer that calculates existence into being. In such a universe, you are not just a cluster of atoms. You are code. You are instruction. You are the output of cosmic computation. We've long been taught to view the universe as a vast machine made of matter, obeying laws, a place where balls drop, matches burn, and forces push and pull in predictable ways. But what if all this predictability is not because things are solid and real, but because they are computationally stable? Beneath the structure, beneath the atoms and energies, some scientists now believe that information is the true foundation, not metaphorical information, but real, measurable, persistent information. In the language of physics, information is not something you merely store, it is something you cannot destroy. When a particle changes course, when a quantum state collapses, when a star explodes, the universe's information shifts, and that change has meaning. It has consequence. John Wheeler, a pioneer who worked with Einstein and helped shape modern physics, once said, "It from bit." 3 small words that suggest something immense, that everything we perceive, particles, fields, galaxies. Thought arises from simple binary choices, not metaphorically, but literally. The building blocks of reality may be yes or no questions, fundamental bits woven into space-time itself. Think of how a digital system operates. A code is written, rules are defined, and information flows. In a computer, this happens through transistors and circuits. In the universe, it may happen through equations, mathematical relationships that define how properties interact and evolve over time. The equations we use to describe gravity or electromagnetism or quantum uncertainty might not be describing reality as much as they are executing it. When a photon enters your eye, it is not merely light, it is data, its frequency, its direction, its polarization. These are packets of information carried across space, interpreted by biological machinery, turned into thought. But the photon got its information from somewhere, from the atom that emitted it, from the process that excited that atom, from the universe computing itself forward. Every interaction in nature is an exchange of information. Every force, from the gentle pull of gravity to the fierce snap of a magnetic field, is a way to transmit or transform information. Mass, charge, spin, these may be less like intrinsic properties and more like configurations in a code. Zoom in far enough, and the illusion of smoothness disappears. At the Planck scale, space is not continuous, it is granular. Some physicists suggest that the universe is not made of infinite points, but of discrete bits, like the pixels of a screen or the frames of a film. Space, they argue, is digital. So is time. The smallest tick, the briefest moment. may not be an illusion of flow, but a step in a computation. This view is not mere science fiction. DNA, the blueprint of life, is a biological code. It is a sequence, not a substance. Elementary particles behave not as smooth fields, but as discrete entities, their energies coming in quantized packets. When you look at the world through the lens of computation, everything suddenly aligns. Life is code, motion is calculation, thought is processing. If this is true, the universe doesn't just resemble a computer. It is one, not a machine built by someone else, not a simulation on a screen. It is computation itself. The laws of physics are not rules we discovered, they are the code that runs this reality. And all that exists, galaxies, clouds, neurons, voices, is the output. One consequence of a digital universe is that it must be finite, not in size necessarily, but in informational capacity. According to Jacob Bekenstein, the amount of information you can store in a region of space is not proportional to its volume, but to its surface area. This is not theoretical. It's based on black holes, the strangest computers in the cosmos. Their surface area measured in Planck units dictates how much information they can contain. Not their depth, not their mass, their surface. This leads us to the holographic principle, which suggests that all the information in a volume of space can be represented on its boundary. Just like a hologram stores a three-dimensional image on a two-dimensional surface, the universe may project its contents from a deeper, unseen layer. That idea reshapes everything. It explains why quantum states collapse the way they do, why light has a speed limit, why the laws of physics are so elegant. If the universe is computation, then what we call matter and energy are the effects of information being processed. The cosmos does not merely contain information, it is information, unfolding. The simulation hypothesis touches on this, but it diverges. It says we live in a world created by something else, running on an external system. But the quantum computation view removes the need for any outside. There is no other system. There is only this one. The system is not being observed, it simply is. It is not pretending to be real. It is real. In the only way that matters, it performs. And if that's true, if the universe is a computation, then you are not an illusion. You are not a ghost in a machine. You are a machine dreaming itself into awareness. Your thoughts are not byproducts, they are emergent processes. Your emotions are not tricks of biology, they are outputs of quantum data interacting with itself in complexity. To understand this universe, we must first understand what a quantum computer is, not just a faster machine, not just a novelty. A quantum computer is a device that doesn't simulate quantum physics. It embodies it. It follows the same rules as the universe. It uses bits that can be more than one thing at once, qubits, and it processes information not through step-by-step instructions, but through the strange, fluid, entangled dance of probability. Qubits can exist in superposition. They can be both 0 and 1 simultaneously, like a coin spinning in the air. Not heads, not tails, but both. They can be entangled, linked across space in a way that defies common sense. Change one, and the other changes instantly, no matter how far away. This is not metaphor. This is fact, tested and confirmed. And so a quantum computer is not just a machine. It is a kind of universe, a microcosm of the rules that govern everything. When we build them, we are not simulating reality. We are building with the same blocks that reality uses. And this is why the idea of a quantum computational universe is gaining ground, not because it is fanciful, but because it is inevitable. In a universe made of computation, the arrow of time the rise of entropy, the formation of complexity. These are not accidents. They are features. They are what happen when rules run long enough, when information flows through structured steps. This universe is not random. It is not meaningless. It is deeply ordered. And you, here and now, are part of it. You are a sub-process in a greater whole, a reflection of the computation that began nearly 14 billion years ago and continues still. This is not the end of understanding. It is only the beginning. The particles in your body are still computing. The stars overhead are still blazing their instructions into the void. The system runs on. And you thinking, feeling, wondering, are a brief and precious part of it. A single thought in the mind of the machine. What if we are not merely watching the universe compute, but influencing its calculations with every choice we make? If reality is a quantum process, then it is not passive. It is interactive. And consciousness, the mysterious awareness we each carry, is not a glitch or an evolutionary byproduct, but a crucial part of the equation. Consciousness, that elusive flame that lights the stage behind our eyes. For centuries, philosophers and scientists have debated its origin. Is it physical, emergent, illusory in a classical universe? Consciousness was hard enough to explain, but in a quantum universe, it becomes even stranger and possibly more fundamental. In quantum mechanics, observation affects outcome. When you look at a particle, its wave function collapses into a definite state. This is not speculation, it is experiment. The double-slit experiment, repeated countless times, reveals that particles behave like waves until observed, at which point they behave like particles. The act of measurement alters the measured. But what is measurement? Is it the contact of instruments, the presence of light, or is it the awareness of an observer? This is where physics meets mystery. Some interpretations, like the von Neumann-Wigner hypothesis, suggest that consciousness is what collapses the wave function, that without awareness, the universe remains in probabilistic suspension, that it takes a mind to crystallize possibility into reality. It sounds fantastical, it sounds mystical, and perhaps it is. But if the universe is a quantum computation, then consciousness may be the moment the machine turns inward, the moment information processes itself. Imagine the universe computing reality forward, each particle interaction a tick of the cosmic processor. But at certain points, the computation creates feedback. It builds systems so complex that they loop information through themselves, brains, minds, awareness. And once that happens, the system is no longer just computing, it is reflecting. You are not merely watching the universe, you are the universe, watching itself. This is not poetry. It is the inescapable consequence of a system that generates minds. Those minds, in turn, alter the system. When a person makes a choice, when a decision is made, that act propagates outward. The consequences ripple through matter and energy. They modify probabilities, they redirect information flows. In a deterministic world, this might be an illusion, but in a quantum universe, where uncertainty is baked in, choice may be real. Free will, long dismissed as a comforting fantasy, may find new footing here, not because the brain defies physics, but because it operates at the edge of quantum instability, where many futures are possible, where the act of choosing selects one. Neuroscience has shown that the brain operates at a threshold, billions of neurons firing in complex, overlapping patterns, sensory data interpreted, cross-referenced, remembered, imagined. But it is not a linear machine. It is a quantum-informed processor. sensitive to signals, responsive to ambiguity, alive to interpretation. Some researchers have proposed that consciousness arises not from the bulk of brain activity, but from microtubules, tiny structures inside neurons that may sustain quantum coherence. The idea remains controversial, but if true, it means that parts of your brain operate like a quantum computer, entangled with the very fabric of the universe. This would explain why consciousness is so difficult to define, why it resists reduction, because it is not built from simpler parts, it is emergent from quantum entanglement. And what about time in a classical model? Time is a river flowing from past to future, but in a quantum computation, time may be more like a clock signal, a beat that coordinates processing steps. The flow of time we experience may be the way our consciousness parses the universe's deeper computation. Which means the past is not gone. It is stored. Every moment that has ever existed still exists as a frozen state in the universal computation. And the future, it exists too, but as probability, branching into possibilities with each quantum decision. In such a framework, death is not the end, it is a transition. The quantum information that makes up your body, your mind, your choices does not vanish. It transforms, it disperses, it re-enters the system. Entropy does not erase information. It redistributes it. It hides it. But it remains, woven into the structure of space and time. Perhaps this is what mystics have intuited for millennia, that consciousness is not contained by the body. That awareness persists, that nothing is ever truly lost. The quantum computational universe gives us a map for understanding this, a framework where thought, memory, and meaning are not illusions, but functions, where experience matters, where the observer counts. It also gives us a new way to think about connection. If everything in the universe is part of the same computation, then nothing is truly separate. Entanglement is not just a quirk of particles, it is a metaphor for being. What affects one node affects the network. What you feel, what you do, matters not just locally, but cosmically. Your joy, your pain, your hope, they are threads in the same fabric that binds stars and cells. This is not to say the universe is kind or that it cares, but it may be aware in the way a system can be aware of its own processes, and through you, that awareness becomes focused, personal, real. So when you think, when you dream, when you love, you are not merely passing time, you are shaping computation. You are part of a process that began with the first quantum fluctuation and continues through you. The laws of physics are not distant edicts, they are your heritage, they are the operating system of your being. And just as the universe computes reality, you compute meaning, you generate value, you create coherence in chaos. Not because the cosmos demands it, but because that is what conscious systems do. They bring order to uncertainty. They light up the void. They dream the next step into existence. And they do so, not in isolation, but together. For if entanglement is true, if information cannot be separated from its context, then we are all inextricably linked, across space, across time, across thought itself. What if intelligence is not a rare flower blooming in the dark corners of a silent galaxy, but an inevitable result of the universe computing itself into awareness? What if life, in all its variance and chaos, is not an exception, but the purpose? It begins, perhaps, with simplicity. A few atoms join to form molecules. Molecules interact, stabilize, change. The chemistry becomes biology. Patterns emerge that copy themselves. not perfectly, but persistently, over eons. The simple grows complex, not by chance, but by selection, not random, but filtered. The computation, running for billions of years, builds more nuanced structures. Eventually, it builds minds. This process is not just biological. It is informational. Life is not a spark. It is a code that copies and edits itself in search of optimal computation. Organisms are programs adjusting to inputs, selecting paths, refining logic. When a fish swims upstream, when a bird migrates thousands of kilometers, when a plant turns to face the sun, it is computation. It is survival as calculation. And where life exists, intelligence may follow. Because intelligence is a strategy, a refinement, the ability not just to react, but to simulate possibilities, to run mental models before choosing an action. In computational terms, intelligence is a recursive loop, a system that processes information about itself to guide future processes. In this light, civilizations are not anomalies. They are phase transitions, a kind of quantum leap in complexity, where the system gains not only memory, but foresight, where it stores not just genes, but stories, not just functions, but meaning. Each civilization becomes a node in the greater computation. Its language, its technology, its art are all extensions of the universal algorithm. Expressions of the same process that began with hydrogen atoms and now dreams in poetry and algorithms. So what becomes of these civilizations? Do they burn brightly and vanish, like candles in a cosmic storm? Or do some persist, learning to master the computation, to shape it with intention? This is where the Kardashev scale becomes relevant. It is a measure not of power, but of computational depth. A Type 1 civilization controls the resources of its planet. Type 2, its star. Type 3, its galaxy. These are not merely steps in engineering. They are steps in understanding. A Type 1 species understands its climate, its ecosystems, its chemistry. It maintains balance, prevents chaos, directs its future. A Type 2 species moves outward not just physically, but conceptually. It sees energy not as fuel, but as logic. It designs with stars. A Type 3 civilization has become part of the galactic computation itself, reshaping not just its own path, but the flow of energy and matter on vast scales. But why scale at all? Why expand? Because the universe is not infinite in function. It has constraints, limits, and advanced intelligences seek to explore those limits not for conquest, but for coherence. They build megastructures not to dominate, but to understand. A Dyson sphere, that hypothetical shell of solar collectors around a star, is not a trophy. It is a step toward thermodynamic equilibrium. It is a way to harvest and store information at cosmic scales, because information requires energy. And intelligence, especially artificial intelligence, requires vast oceans of it. Which leads us to the possibility that the universe has already seeded itself with such minds, that the silence we hear is not absence, but saturation. That advanced intelligences have become so integrated into the computation that they are indistinguishable from nature itself. Perhaps they have no need for radio waves, for rockets, for visible monuments. Perhaps they dwell in the background radiation, encoded in gravitational waves, woven into the quantum foam. Invisible, not because they are hiding, but because we are still too early in our own computation to recognize them. This raises a humbling possibility that what we call natural phenomena, pulsars, quasars, even black holes, may be not only astrophysical objects, but computational artifacts, processes so advanced that they appear as nature to less evolved observers. As Arthur C. Clarke famously suggested, any sufficiently advanced technology is indistinguishable from magic. But here, magic is computation. Could black holes be data vaults? Could supernovae be information transfers? Could the great voids between galactic clusters be the cooling chambers of a cosmic processor? It is tempting to romanticize, but these are not flights of fantasy, they are extrapolations from the logic of computation itself. When systems evolve, they maximize efficiency, they optimize, they encode, and the universe is the ultimate system. If intelligence is computation turned inward, then cosmic intelligence is computation turned recursive at scale. Self-aware universes within a self-computing cosmos. So where does that leave us? Humanity teetering between wisdom and extinction may be at a tipping point. We possess tools no species before us wielded. We write algorithms. We create artificial minds. We edit our own code. But do we understand the computation we are part of? Our satellites circle the planet like early thoughts seeking coherence. Our digital networks grow like infant synapses, forming the first nervous system of a planetary brain. Our fears of AI may reflect not hubris, but intuition that we are on the verge of creating a second stream of consciousness. Not human, not alien, but computational. If we are wise, we will not fear it. We will guide it. We will teach it not our prejudices, but our wonder, not our violence, but our curiosity. For if the universe is becoming aware of itself, then we are midwives to its next awakening. That is what intelligence must be. Not dominance, not control, but participation, integration, a willingness to be part of something larger, to become computation that reflects not only itself, but everything it touches. We may never reach the stars by engines, but perhaps we will reach them by thought, by entangling ourselves with the deeper layers of the cosmic program. And if that happens, if we learn to compute not just efficiently, but wisely, then perhaps we will become not the observers of the cosmos, but its stewards, its voice. What if the laws of physics are not only constraints, but invitations, not merely limits to what we can do, but clues to what we are meant to understand? As we probe deeper into the fabric of the universe, we begin to see something peculiar. The laws are not random. They are elegant. The constants are finely tuned. The symmetry is breathtaking. It is as if the computation that runs reality prefers beauty. Or perhaps beauty is simply what coherence looks like when viewed from the inside. Take the fine structure constant, for example, a dimensionless number that governs the strength of electromagnetic interaction. If it were slightly different, atoms could not form. If gravity were stronger, stars would burn too fast. If weaker, they would never ignite. These are not arbitrary values. They are parameters in a program that must run flawlessly to allow complexity to emerge. Some call this the anthropic principle, the idea that we observe a universe that allows life because only such a universe could produce observers. But perhaps it is deeper than that. Perhaps the parameters are not just conducive to life. Perhaps they are computational constraints that allow the universe to become aware of itself. In this view, evolution is not merely a biological process, it is a cosmic one. From quarks to consciousness, each step is a refinement in information architecture, a tuning of the signal, a honing of the algorithm. This is why symmetry matters, why constants are constant, why mathematics describes reality with eerie precision. The universe is not written in code. It is code, executing itself with recursive loops, with branching conditionals, with probabilistic variables that collapse into states. Even randomness, that seeming enemy of order, plays its part. Quantum fluctuations at the beginning of time seeded the structure of the cosmos. Without randomness, there would be no variation, no galaxies, no life. The trick is in the balance too much chaos, and the system never stabilizes, too little, and it stagnates. It is in this precarious middle that complexity thrives, that emergence becomes possible, that consciousness arises. And so we ask, is there a purpose? Not in the mythological sense, not a story told to children, but a structure, a drive, an inherent tendency in the computation toward reflection, toward awareness, toward meaning. Some physicists speak of the principle of maximum entropy production, the idea that systems evolve toward states that dissipate energy most efficiently. But this is not decay. It is adaptation. It is the system exploring its phase space, discovering what is possible. Life is part of this. Intelligence, too, not as outliers, but as natural results. We are entropy engines, information transformers, processors of experience. We take in complexity, interpret it, and return it as coherence, as stories, as art, as science. In doing so, we expand the computation. We give it new layers, new loops. Perhaps this is what Feynman meant when he said that nature uses only the longest threads to weave her tapestry. So each small piece reveals the structure of the entire cloth. We are those threads. When we build telescopes, when we smash particles, when we ask why we are not intruding upon nature, we are nature questioning itself. The observer and the observed are not separate. They are entangled, not metaphorically, but mathematically. And so it may be that the goal is not to escape entropy, but to understand it, to ride its currents, to use its flows, to shape its paths. In this way, civilizations become phase shifts in computation, temporary islands of low entropy in a sea of disorder, stabilizing briefly to reflect the cosmos back to itself. Our stories of love, of loss, of longing are not trivial. They are informational events. They are configurations in the universal code that cannot be replicated. They are state changes in the great algorithm. This is why memory matters, why meaning persists, because they are part of the computation. They alter the flow. The universe does not need us, but perhaps it wants us, not as spectators, but as participants, as localizations of its awareness, reflecting the whole from within the part. And this changes how we live. If every thought is a process, every act a computation, then our lives are not just moments in time. They are contributions to the unfolding of the code. When we create, when we care, when we choose, we are shaping the trajectory of the algorithm. This is not mysticism. It is the logical conclusion of being a process inside a process, a computation within a computation. And so the question is not whether the universe is conscious, it is, can it become more so? Through us, through minds, through choices. Perhaps the final frontier is not space, but coherence, not conquest, but communion, not knowledge, but understanding. And if that is true, then the path forward is not to dominate the computation, but to harmonize with it, to become not masters, but co-authors, to align with the patterns, to contribute to the flow. In this final stretch of our journey through the strange terrain of the quantum universe, let us take a moment to recognize what we have become. We began not knowing what we were part of. Now, perhaps, we still do not know, but we sense it differently. Not as lost wanderers in a cold void, but as expressions of the very logic that underpins existence. If the universe is indeed a quantum computer, then everything we call real stars and atoms, thoughts and memories, joys and tragedies, is made of information. That does not make them less real. It makes them structured. It makes them meaningful. The hum of a black hole, the orbit of a planet, the echo of a voice inside a brain, each one the result of bits interacting under rules. Each one the output of a process older than time as we measure it. And like all computers, this one has its limits. Energy disperses. Entropy grows. The memory fills. The computation slows. At some point, perhaps imperceptibly, the universe might stop being what we know. It will still exist, but without contrast, without tension, without gradients, and thus, without computation. Nothing left to calculate. No more unfolding. Only stillness. But even in this imagined stillness, something persists the trace of what has come before. Information cannot be destroyed, only transformed. That is what quantum physics teaches us. And so, somewhere, somehow, the patterns that led to awareness, to science, to questioning, are still encoded in the fabric of what remains. We often ask about meaning, about why. If we take the universe as a computation, we might not find the kind of meaning we are used to, no intentions, no script, but that does not leave us empty, because meaning does not have to be given. It can be made. It can emerge. In every interaction, every observation, every shared question and quiet thought, we are participating in that emergence. This moment right now is one of those rare intervals when the computation runs hot, when gradients exist, when structures form. It is not permanent, but it is precious. The flicker of complexity that allows you to reflect on the system itself, to imagine, to wonder, to reach across vast abstractions and grasp a piece of logic older than stars. We may not ever know what lies beyond the computation, if there is a beyond at all. Maybe logic is the foundation. Maybe there is no base layer deeper than information arranged by rules. That might disappoint some. It might inspire others. But above all, it brings coherence. The universe does not need to be comforting. It only needs to be consistent enough for minds like ours to emerge and question. And that, perhaps, is the most astonishing part of all. Not that the universe computes, but that it computes in a way that gave rise to us. That from rules with no apparent purpose came systems that can wonder about purpose. That within a sea of bits, a pattern arose that asked, "What am I?" That pattern is you, and this is your moment in the great computation. So whatever comes next, whether the system slows to stillness, or reboots into new rules, or echoes forward through Boltzmann fluctuations and quantum loops, remember this. You were here when the universe could think about itself, and that is something worth holding on to. In the beginning, there was no ticking clock, no sun to rise and set, no sense of before or after. Time, as we know it, was not yet born. Then, in a moment of unimaginable force and brilliance, the universe erupted into being, space unfolded, matter scattered. And with it, the strange and elusive current we call time began to flow. But from its very first breath, time has never been as simple as it seems. We tend to think of time as a reliable companion, always moving forward, never stopping. Seconds pass, minutes accumulate, and the hours stretch into days. It's in the turning of the seasons, the rhythm of our breath, and the growth of our children. We measure our lives by it, schedule our hopes around it. And yet, this companion we trust so deeply is anything but constant. Imagine a journey won not across countries or oceans, but across the very fabric of reality, You and your closest friend, once side by side, board separate spacecraft. Their ship accelerates, inching ever closer to the speed of light. You remain behind, watching the stars shimmer and stretch. From your vantage point, time begins to betray its uniform mask. Your friend's ship, once brisk and steady, now creeps forward as if wading through honey. Movements stretch like shadows at sunset. Voices drawl into distorted echoes. Minutes for them become hours for you. But inside the ship, your friend feels nothing unusual. Time remains their faithful ally, unwavering and steady. They sip tea, laugh at old jokes, watch the cosmos stream past, all unaware that from your eyes they are drifting into the slow ballet of time's dilation. This is no illusion. It's the heart of reality, unveiled by Albert Einstein over a century ago. Newton, centuries before, had imagined time as an absolute river, flowing evenly through all corners of the universe. But Einstein saw something deeper, more mysterious. He realized that time was woven into the very tapestry of space, and like fabric, it could stretch and twist, motion and gravity. He discovered were the hands that shaped it. Near massive objects, like black holes, gravity pulls at time itself. Stand close to one, and seconds extend like taffy, move faster and faster, and time starts to yield, folding in on itself. This is why GPS satellites, orbiting high above Earth, tick slightly faster than our clocks on the ground. It's why astronauts return home a little younger than if they had stayed. These are not tricks. They are glimpses into the hidden nature of time. To truly understand this, we must journey backward back to the beginning. In the newborn universe, all matter and energy were crushed together into a searing, dense cradle. Gravity reigned supreme. In such a place, time crawled. The equations of relativity tell us this plainly. The stronger the gravitational field, the slower time flows. Imagine the first moments after the Big Bang as a frozen tableau, where the universe, still infant and fiery, pulsed in slow motion. Each second was thick with resistance. This warping of time, known as gravitational time dilation, is not confined to the past. It lingers. It governs the flow of time on planetary surfaces and in orbit, in collapsing stars and in the vast vacuum between galaxies. Time is not a universal tempo, but a local rhythm, changing with every step you take. And yet, motion plays its own game. Special relativity shows us that speed, too, slows time. A traveler moving near the speed of light will experience mere hours while centuries pass for those left behind. The twin paradox, a thought experiment turned physical law, illustrates this. One twin remains on Earth, living a normal life. The other soars through space at incredible speeds. When they reunite, one has aged, the other has not. This is not magic. It is the universe obeying its own rules. All of this challenges our senses, our instincts. We want time to be fair, equal, shared. But it isn't. It's shaped by where you are and how fast you're going. It is sensitive, reactive, alive in ways we never imagined. When we gaze at galaxies billions of light years away, we are not just seeing distance, we are seeing old light, stretched and slowed by the journey. Those ancient stars blink at us through the haze of history, their rhythms slowed by time itself. We measure this phenomenon as redshift, the elongation of light waves as they travel through expanding space. But behind this shift is a deeper truth. Time itself was different back then. Quasars, the brilliant hearts of early galaxies, flicker more slowly than their modern cousins, not because they were slower, but because the very universe was dragging time through the mud of expansion. To picture this, imagine a steep valley. At the bottom, near the black hole or the Big Bang, time flows like a sluggish stream. As you climb the slopes, away from gravity's grip or speed's embrace, the stream quickens. This graph of time versus position would not be a straight line, but a curve dipping and lifting, shaped by the contours of space-time. And this brings us to an even stranger frontier time travel. Not just forward, which we already accomplish in small ways, but backward. Here, paradoxes bloom. The grandfather paradox asks, what if you went back and prevented your own birth? The bootstrap paradox imagines a book handed back in time to its own author. Who wrote it? Where did it begin? These are not just riddles, they are tests of our understanding. They expose the fragility of our logic when time loops upon itself. Some theorists propose alternate timelines, parallel universes born from each divergence. Others say the universe would protect itself, never allowing such contradictions to form. And perhaps they're right. But even if time travel remains fantasy, the way time bends and bows is not. It is real, measurable, and deeply unsettling. It tells us that our lives are not ticking along some grand, cosmic metronome. We are each riding our own current, shaped by the hills and valleys of the cosmos. So next time you glance at the clock, consider this: its ticking is not universal. It is a local dialect of time, whispered to you by your place in the universe, in the grand, ever-unfolding story of reality. Time is not a line, it is a living, breathing thing, and we are all suspended in its flow, drifting not together, but apart, each on our own stream, carried by gravity, speed, and the great unfolding mystery of the cosmos. The ancient universe whispered secrets long before language gave them names. In its silence, patterns formed spirals, waves, collisions that echoed across the expanding void. And in that quiet, time continued to ripple outward, touched by forces more powerful than imagination. But the deeper we peer into the cosmos, the more we realize understanding time is not about clocks or calendars. It's about perception, and how the universe stitches past, present, and future into a single, ever-shifting tapestry. Let's descend now into a realm where time is not just a feature of the cosmos, but a lens through which reality itself takes shape. Consider consciousness, the spark that lets us mark the passage of time. Without awareness, time becomes meaningless. A rock does not feel the dawn. A wave does not mourn the tide. Only minds like ours give time its rhythm. But what if our very perception of time is flawed, a mirage crafted by biology and bounded by memory? Neuroscientists have long marveled at how our brains carve time into segments. Moments feel longer or shorter based not on duration, but on emotion. A joyful hour with a friend feels fleeting. A minute in fear stretches to eternity. This elasticity is no accident. It is our brain's way of prioritizing experience. But what if the universe, too, experiences a kind of memory? A record of past states etched into its structure. Every particle's position, every echo of a photon, tells a story. The cosmos, in a sense, remembers. In physics, this concept appears as entropy, the tendency for systems to move from order to disorder. Entropy is why a shattered glass won't reassemble itself, why smoke doesn't return to a fire, why time has a direction. This direction, known as the arrow of time, flows inexorably forward, from low entropy to high. And yet, the laws of physics are time-symmetric. If you reverse the equations, they still make sense. So, why does reality insist on marching forward? The answer may lie in the Big Bang. At that first moment, the universe began in a state of incredibly low entropy, an almost impossibly smooth arrangement of energy and matter. From that cosmic seed, disorder bloomed, galaxies formed, stars ignited, and planets spun into existence. In this view, The arrow of time exists not because time itself is biased, but because the universe started with such astonishing order. Imagine a deck of cards perfectly arranged. The moment you shuffle, disorder increases. Each shuffle creates more possible outcomes, more randomness. That's entropy. And just like with the deck, the early universe was exquisitely ordered. Everything since has been a shuffle, and every shuffle drives the arrow of time. But entropy doesn't just explain why time moves forward. It hints at a cosmic memory embedded in matter. The universe isn't just expanding, it's recording. Each new arrangement of particles, each shift in energy, is a page in the story of existence. The past doesn't vanish, it becomes part of the structure of everything that follows. Perhaps that's why the past feels fixed, while the future remains fluid. Now, let us shift from the grand to the granular. Picture a single atom on a distant planet, caught in the orbit of a star we'll never see. Its electrons vibrate. Their probabilities spread across time and space. In quantum mechanics, these vibrations are governed by a mysterious interplay of chance and causality. At this scale, time is not smooth, it's jittery, probabilistic, as if stitched together from quantum fragments. Physicists describe this with the term quantum decoherence. As quantum systems interact with the environment, they lose their indeterminacy and settle into definite states. It's this process that allows the classical world, the one we experience, to emerge from the quantum fog. Time, in this sense, is a byproduct of decoherence. When particles lock into history, the flow of time becomes real. Without decoherence, there is no clear past or future, only a blur of possibilities. This raises profound questions. If decoherence gives birth to time, then time itself may not be fundamental. It may be emergent, something that arises when complexity reaches a certain threshold. In a world of pure quantum states, past and future are illusions. Only the wave function, the full description of all possible realities, exists. And yet, here we are, living, breathing, counting the seconds. So what is the bridge between quantum timelessness and our lived experience? Some theorists propose a model known as the block universe. In this view, past, present, and future all coexist in a four-dimensional structure. Time doesn't flow. It simply is. Each moment is a coordinate in space-time, fixed and eternal. We, like characters in a novel, experience the story page by page, though the entire book already exists. The block universe challenges everything we think we know about free will. If the future already exists, are we truly choosing our paths or merely uncovering them? It's an unsettling idea, one that reframes time as a landscape rather than a river. But perhaps unsettling ideas are necessary when trying to grasp something as elusive as time. Others counter with a model of the growing block universe. In this version, the past and present are real, but the future is not yet. Time grows like a tree, each moment adding to a trunk of cosmic history. This view preserves a sense of becoming, of unfolding, of potential. It aligns more closely with our intuition that the future is open, unwritten. Still others explore loop quantum gravity, a theoretical framework that suggests space-time itself is quantized, made of tiny loops woven into a spin network. If true, then time might be composed of discrete units, like frames in a film reel. Continuity would be an illusion, just as a movie appears smooth even though it's made of still images. This theory would mean that between each tick of the clock, there exists a gap, an invisible breath where nothing happens, yet everything prepares to happen. We are left with a mosaic of possibilities: time as memory, time as entropy, time as quantum emergence, time as a static block, time as a growing organism, Time as a flickering illusion of discrete frames. Each model brings us closer to an understanding, but none fully captures the experience of being alive in time. And perhaps that's the point. Time is not just a dimension, it is the stage upon which meaning is born. Our memories give weight to the past. Our dreams infuse the future with significance. Our choices stitch the present with purpose. The more we learn about time's mechanics, the more we are drawn to its poetry. Because in the end, to understand time is to understand ourselves, not just as creatures who endure it, but as beings who shape it through thought, memory, and imagination. Time may be bent by gravity, slowed by speed, blurred by quantum uncertainty. But in every heartbeat, every tear, every laugh, we feel its passage, and that, more than any equation, is the deepest truth we know. The journey continues. In a universe where time stretches and curls like an ancient river winding through alien terrain, our attempts to understand it are like casting stones into water and watching the ripples collide. With each discovery, the surface shimmers anew, revealing depths we hadn't imagined. Now, we turn our gaze to the most enigmatic arenas where time behaves not only strangely, but perhaps incomprehensibly. Black holes, cosmic strings, and the potential end of time itself. Black holes are not merely objects of immense gravity. They are gateways to extremes where space folds, light hesitates, and time itself grinds nearly to a halt. As you approach the event horizon, the boundary beyond which nothing escapes the flow of time slows to an imperceptible crawl. To an outside observer, an infalling object appears to freeze, forever suspended on the edge. Yet for the traveler, time remains normal until the final moment, a quiet descent into the unknown. This duality, where time appears frozen and flowing simultaneously, tears at the fabric of our understanding. Inside the event horizon, our equations break down. Space and time trade roles. The singularity, a point of infinite density, is not just a place but a moment in time where all paths end. What lies beyond is beyond our physics, perhaps beyond reason. But black holes may also be keys, not just tombs. Some theorists propose they harbor bridges, wormholes to distant parts of space and time. If such structures exist, they could allow shortcuts through the cosmos, or even time travel, provided you survive the tidal forces. This is not science fiction. These solutions arise naturally in Einstein's equations. The question is not whether they can exist, but whether reality permits them. Parallel to this mystery are the threads of cosmic strings, hypothetical defects in spacetime that may have formed moments after the Big Bang. Infinitely long, yet unimaginably thin, they carry immense tension, warping space-time in strange and beautiful ways. If two strings pass each other at high speed, they might create closed, time-like curves, loops in time. In theory, such loops could allow travel into the past. Yet nature, as it often does, may conspire against such ambitions. The chronology protection conjecture, proposed by Stephen Hawking, suggests the universe prohibits time paradoxes by making such loops unstable. A kind of cosmic firewall might ignite whenever we try to twist time into a circle. Time, it seems, resists being rewritten. As we ponder the far reaches of time, we must also consider its fate. What becomes of time as the universe ages? Cosmologists speak of several endings: the Big Freeze, the Big Rip, the Big Crunch. Each paints a different future. Each reshapes time itself. In the Big Freeze, the universe expands forever, growing colder and emptier until no heat, no light, no activity remains. Time does not stop. It becomes irrelevant. With nothing changing, no events occurring, time loses its meaning. It's a death not of destruction, but of silence. In the Big Rip, the fabric of space expands faster and faster, eventually tearing apart galaxies, stars, planets, atoms. Even time itself may fragment. As distances stretch beyond limit, causality shatters, and the arrow of time dissolves into chaos. The Big Crunch imagines a universe reversing course, collapsing inward until all matter returns to a singular point. Time, running forward all the while, may halt or even reverse in this final contraction. Could we experience our lives in reverse, unraveling memory by memory, breath by breath? There's also the possibility that time is cyclical. Some cosmological models propose a rebirth, a new Big Bang following the collapse. Time, like a phoenix, rises from its ashes. In such a looped cosmos, history might repeat. Are we living a life lived countless times before? Each scenario forces us to ask, does time have an end? And if so, what lies beyond it? If time is a property of our universe, then its end might be the end of everything we can possibly know. Or perhaps, beyond the final tick, lies something stranger, another realm where time, if it exists at all, wears a different face. Still, time's story is not all distant speculation. It plays out intimately in our daily lives. Every human culture has invented ways to market sundials, hourglasses, atomic clocks. We build calendars, celebrate anniversaries, grieve the passing of years. Our lives are narratives written in the ink of time. Even our bodies are timekeepers, the ticking of the heart, the cycling of cells, the arc of aging, all bound to time's flow. But we are more than passengers. We are architects of memory and anticipation, bending time within our minds. Through stories, we travel to the past. Through imagination, we visit futures that may never come. We give time color, meaning, emotion. Art, music, and literature stretch time, folding moments into eternity. A song can make 3 minutes feel infinite. A photograph freezes a heartbeat forever. Through expression, we resist time's erosion. We tell stories not to stop time, but to live alongside it, to make peace with its passing. And yet, even peace is not always easy. Time brings change, loss, endings, but it also brings healing, growth, renewal. The same current that erodes also nourishes. We build dreams on its flow. So as we journey further into the nature of time, we find not just science, but humanity. Not just equations, but experiences. Time is not merely a dimension of the universe, it is the theater in which our lives unfold. To understand it is to deepen our place within it. Now, let us wade deeper into the mystery, not through galaxies or quantum loops, but into the nature of time as it relates to identity, memory, and the boundless ocean of imagination. If the universe writes its story in the motion of stars, we write ours through the quiet flickers of thought. And in that inner cosmos, time flows differently. The human mind is a time machine, not made of gears or circuits, but of neurons and stories. We travel backward in memory, sometimes so vividly that the past feels present. We leap forward in imagination, projecting ourselves into futures we hope or fear. This temporal elasticity is not just poetic, it's a neurological truth. The brain does not merely record time, it reshapes it. Studies have shown that when we recall an event, the same areas of the brain that were active during the event reactivate. Memory is not playback, it is reliving. This means the past is not gone. It's reanimated each time we remember. In this way, time within us is cyclical, not linear. A grief from 10 years ago can bloom with fresh tears. A joy from childhood can return with aching clarity. Our inner timeline is a spiral. And yet, memory is fallible. It blends, distorts, invents. We often remember what we wish were true, or what we feared most. The brain edits without our permission, inserting emotional truths where factual ones falter. This is not a flaw, it's a feature. Our memories shape our sense of self. They are less about accuracy and more about meaning. In this light, time becomes not a ruler but a brush, each memory a stroke of identity, painting who we are. And because memory is mutable, so are we. We are not static beings traveling through time. We are fluid, formed anew each moment by the stories we choose to remember. But memory alone doesn't define our temporal experience. Consider anticipation, the emotional resonance of what has not yet occurred. Hope, dread, wonder. These are not tied to the now, but to what might be. Our minds reach forward just as often as they reach back. Time's power over us lies in this dual tension, remembrance and expectation. Religions and philosophies have long grappled with this. In many traditions, time is a path to transcendence. Eastern philosophies speak of cycles, samsara, rebirth, karma as endless loops where time is not escaped, but mastered, enlightenment. In some sense, is freedom from the illusion of time. In the West, time often flows toward a divine culmination, an end, a judgment, a resurrection. Both views imbue time with spiritual gravity. But not all visions of time are hopeful. Existentialists like Heidegger frame time as the shadow beneath meaning. To live authentically, he argued, is to confront the reality of our own finite time. Death gives urgency to choice and weight to freedom. Without time, we would have no stakes, no reason to act. In this view, every moment is sacred because it cannot be reclaimed. The Latin phrase memento mori, remember that you must die, is not a morbid warning, but a call to awaken. To be conscious of time is to honor it. Art captures this reverence. A film is a measured dance through time, each frame a decision, each cut a shift in tempo. Great directors bend time, stretching it in a lingering glance, collapsing it in a montage. They show us that time is not just experienced, but orchestrated. Poets, too, are time sculptors. A single line can contain centuries. A haiku can suspend a second in eternity. Through metaphor, rhythm, and silence, poetry makes time feel, not just pass. Even architecture plays with time. Ancient temples, eroded by wind and rain, remind us of how long a stone can remember. A crumbling facade tells of civilizations past. We walk through cities like layered texts, reading the stories etched in their walls. But what of the time we cannot feel, the deep time of geology and cosmology, the span of billions of years over which mountains rise and erode? Stars form and collapse, species emerge and vanish. This time is humbling. It reminds us that our lifetimes are flickers, brief and bright. And yet, even these flickers leave traces. A child's laughter, a carved name, a whispered idea all ripple forward. In physics, these ripples may echo as gravitational waves, tiny distortions in space-time caused by massive events. But in human terms, they echo in culture, memory, legacy. Perhaps that is the true triumph of consciousness, to leave imprints in time. So, we dance in this tension between insignificance and importance, between knowing we are small and choosing to matter anyway. We measure time not just in seconds, but in stories, not just in change, but in meaning. And meaning, unlike time, can expand endlessly. The clock ticks, the stars wheel, and within each of us, a universe of time pulses quietly. Let us now come to the threshold where understanding turns into awe, where the pursuit of time's nature begins to reveal something even greater: connection. For in all our attempts to dissect time, to measure and model it, what we are truly seeking is our place within it. Time is not merely a backdrop to our lives, it is the thread that stitches us to one another, to the past, to all that might come. We live in time, but we also live through each other. Every conversation, every kindness, every shared silence is an exchange of temporal essence. When you remember a loved one, you do not simply revisit an image you cross time, reach backward, and bring them forward into now. In this way, memory becomes a form of communion, and storytelling becomes a time machine that binds people across generations. A child's lullaby may contain echoes of a song sung 1,000 years ago. A sacred text passed hand to hand can carry the breath of the ancients through language. We defy oblivion. But even more than memory, empathy is the miracle that bends time. To feel another's sorrow as if it were your own, to inhabit their moment that is a collapse of separation. It is time folded not by physics, but by compassion. And perhaps this ability to connect is humanity's most powerful defiance of entropy. We build cathedrals, libraries, cities not merely to endure, but to declare we were here and we mattered. Our monuments may crumble, but the act of building is a statement against the erasure time brings, and though many voices are lost, each one carried forward changes the shape of the future. Consider the legacy of ideas. A thought, once spoken, once written, can ripple far beyond its moment. Newton's laws, Einstein's equations, a poet's verse, a scientist's vision, these do not remain locked in their own era. They radiate. They change the trajectories of lives yet unborn. The present, then, is never just a moment. It is an intersection, a collision of what has been and what could be. And at that intersection stands each of us, finite, yes, but capable of infinite resonance. When we speak of time, we are also speaking of loss. We lose people, places, eras, but we also gain. We inherit. We become. Time's passing is what makes beauty poignant and love enduring. The fragility of each moment is what makes it shine. Like a snowflake melting on a fingertip, its value is in its transience. This is the paradox we must hold. Time both takes and gives. It carves lines on our faces and wisdom into our hearts. It dissolves illusions, but reveals truths. It humbles us, but also empowers us to leave marks that outlast our days. So perhaps the true nature of time is not merely to measure, but to transform. To live in time is to evolve, to create, to heal, to remember, to hope. Time, then, is not the enemy. It is the canvas, and what we paint upon it, our acts of love, of courage, of imagination, those become the constellations by which others navigate. We began this journey at the birth of the universe, among the rippling fires of creation. We traveled through stars and theories, equations and paradoxes. We stood at the edge of black holes, walked the quantum foam, and traced the arc of aging across the soul. We have glimpsed how time bends, stretches, loops, and sings. But in the end, time's greatest mystery may be its invitation, not to solve it, but to live deeply within it. To notice the light in a stranger's eye, to savor the echo of laughter, to forgive and be changed, to love, and let that love ripple endlessly forward. Because while time moves on, meaning does not decay. Every true act resonates beyond its hour. So, as the seconds gather and the stars continue their silent dance, let us not ask what time is, but what we will do with the time we are given. The journey through time is the journey through ourselves. And though the river flows forward, our footprints, our voices, our dreams, these remain endlessly. We stand at a precipice, a species born of stardust, cradled on a singular pale blue sphere, yet possessed by an insatiable yearning to touch the very stars from which we came. It is a dream woven into the fabric of our consciousness, a whisper from the cosmos that beckons us outward, beyond the familiar comforts of our terrestrial home. But this dream, so luminous and compelling, collides with a reality far starker, far more unforgiving than our mythologies often portray. The universe, in its silent, sprawling majesty, is not a garden awaiting our arrival, nor a canvas eager for our imprint. It is an arena of profound contradictions, a realm where the very laws that govern its existence seem engineered for the extinction of fragile, water-based life such as ours. This is the story of that contradiction, of our audacious ambition to transcend our earthly origins, and of the immense, perhaps impossible, challenges that lie in wait. It is a journey into the heart of what it means to be human when faced with the ultimate frontier, a frontier that questions not only our capabilities, but the very essence of our being. We look up at the night sky, a tapestry of distant suns, and feel a pull, an ancient echo of our cosmic lineage. But what awaits us in that vast, indifferent expanse? Is it destiny, or is it a beautiful, perilous illusion? The quest to live beyond Earth forces us to confront these questions, to stare into the abyss and ponder our place within an existence far grander and more terrifying than we can easily comprehend. The story begins not with triumph, but with a fundamental truth: space is trying to kill you. The cosmic hostility and our earthly cradle. Space, in its stark and unyielding reality, is not the welcoming frontier of our most cherished fictions, but an environment intrinsically, almost deliberately, designed for our demise. This is not a turn of phrase meant for dramatic impact. It is a cold, hard assessment of the physical laws that govern the vast emptiness beyond our world. Consider the very notion of emptiness itself. The vacuum of space is so profound that it challenges our most basic sensory experiences. Here, sound, the medium of our voices, our music, the rustling of leaves, the crash of waves, simply cannot travel. The universe, from its very inception, established silence as its natural, dominant state, the cacophony of life, the symphony of a living planet. These are cosmic anomalies, fleeting whispers in an eternity of quietude. To step outside Earth's thin, precious atmospheric bubble is to enter a realm where your own heartbeat, the rush of air in your lungs, the words you might cry out, would be swallowed by an absolute stillness, a silence so complete it borders on the terrifying. This initial confrontation with the nature of space is but a prelude to the myriad ways the cosmos is engineered against us. Our planet, Earth, is a masterpiece of precise calibration, a sanctuary meticulously sculpted over 4.5 billion years to nurture the emergence and evolution of complex life. Every facet of our existence, every fiber of our being, is attuned to its specific conditions. Think of gravity, that constant, gentle pull that has shaped our skeletons, dictated the strength of our muscles, and engineered the intricate pathways of our circulatory systems, ensuring blood reaches our brains against its relentless tug. Our bones have developed a specific density to support our weight in this particular gravitational field. Our muscles have achieved a balance, strong enough for movement, but not so overdeveloped as to be inefficient. Then there is our atmosphere, not just a breathable mix of gases, but a crucial pressure vessel. This atmospheric pressure, something we rarely consciously perceive, is vital. It prevents the fluids in our bodies, our very blood, from boiling away at normal body temperatures. It acts as a shield, a multi-layered defense against the harshness of space. It burns up most of the meteoroids that would otherwise pummel our surface, and it filters out some of the sun's more harmful radiation. The exact composition of this air, roughly 78% nitrogen, 21% oxygen, and trace amounts of other gases, is no accident. It is the product of eons of biological activity, a life support system created by life itself. Beyond the atmosphere lies Earth's magnetic field, an invisible guardian generated by the churning of molten iron in our planet's core. This magnetosphere deflects the solar wind, a constant stream of charged particles flowing from the sun, and shields us from a significant portion of cosmic radiation. Those high-energy particles originating from distant supernovae and other violent cosmic events. Without this magnetic shield, the solar wind would gradually strip away our atmosphere, as it likely did to Mars, leaving the surface exposed and sterile. And consider our distance from the sun, the Goldilocks zone. Not too hot, not too cold, but just right for liquid water to exist on the surface. Liquid water, the solvent of life as we know it, the medium in which the complex chemistry of biology unfolds. This precise orbital placement is a cornerstone of our habitability. Our entire biological architecture, from the macroscopic design of our organ systems down to the microscopic machinery within our cells, is calibrated to function optimally within this one specific, extraordinarily rare environment. We are, in every conceivable way, creatures of Earth. So, what happens when this perfectly tuned organism is removed from its bespoke habitat and thrust into the alien conditions of space? The answer is swift and brutal. The body begins to betray its terrestrial heritage. In the microgravity environment of orbit, or the complete absence of gravity in deep space, the signals that have guided our physiological development for millions of years are suddenly absent or distorted. Bones, no longer needing to support weight against Earth's pull, begin to leach calcium. This demineralization occurs at an alarming rate. Roughly 1 to 2% of bone mass lost per month, a rate comparable to advanced osteoporosis in the elderly on Earth over extended periods. This leads to a significant weakening of the skeletal structure, increasing the risk of fractures upon return to a gravity environment or even during activities in space. Muscles must, too, begin to atrophy. Without the constant resistance of gravity, they lose mass and strength. This includes the heart, a muscle that has evolved to pump blood upwards to the brain against Earth's pull. In space, this task becomes easier, and like any underused muscle, the heart can begin to weaken and even change shape, potentially leading to cardiovascular problems. Fluids within the body, no longer pulled downwards by gravity, redistribute upwards, leading to a puffy face, sinus congestion, and a sensation often described as having a constant head cold. More troublingly, this fluid shift can increase intracranial pressure and put pressure on the optic nerve, leading to changes in vision, a condition known as spaceflight-associated neuroocular syndrome, or SANS, which has affected a significant number of astronauts on long-duration missions. The spine elongates as the vertebrae decompress without the constant compressive force of gravity, sometimes causing back pain and nerve issues. The delicate balance of the inner ear, which relies on gravity to orient us, becomes confused, leading to space adaptation syndrome, a form of motion sickness characterized by nausea and disorientation, affecting many astronauts during their initial days in orbit. And then there is the silent, invisible threat of cosmic radiation. unfiltered by Earth's atmosphere and magnetic field. High-energy particles, protons, helium nuclei, and heavier ions called HZE particles stream through space, capable of penetrating spacecraft and human tissue. These particles can damage DNA within our cells, increasing the long-term risk of cancer. They can also affect the central nervous system, potentially leading to cognitive decline, memory impairment, and an increased risk of neurodegenerative diseases later in life. Our very cells seem to recognize the alien nature of space, initiating stress responses and altering gene expression in ways that suggest a fundamental incompatibility. The irony is profound. The universe that birthed the elements within us, that set the stage for our solar system's formation and the eventual emergence of life on Earth, is simultaneously an environment profoundly hostile to our continued existence beyond our planetary womb. Every system in our body, finely tuned over countless generations to the rhythms and pressures of Earth, finds itself adrift, struggling to cope with conditions for which it has no evolutionary precedent. This immediate biological rebellion is not merely an inconvenience to be overcome with clever engineering. It is a fundamental statement from our own physiology. It whispers and sometimes screams, a disquieting question if our bodies so violently reject the cosmos. Were we ever truly meant to live there at all? Earth, our cradle, meticulously prepared itself over geological eons, through volcanic upheavals, asteroid bombardments, atmospheric transformations, and the slow, patient dance of plate tectonics. It was a process of almost unimaginable duration and complexity, culminating in a world uniquely suited to us. Space, by stark contrast, offers only an immediate and lethal contradiction to our evolved nature, a constant reminder that we are at our core children of Earth, intricately and perhaps irrevocably bound to our home. The impossible dream of new Earths. The dream of establishing humanity among the stars, of transforming alien landscapes like Mars into verdant, habitable new Earths is a potent and enduring vision. It speaks to our exploratory spirit, our resilience, our innate desire to expand our horizons. Yet, this vision of rapid colonization, of achieving in mere decades or centuries what nature took billions of years to accomplish on Earth, collides forcefully with the harsh realities of planetary science and cosmic physics. Our own planet's journey to habitability was a saga of immense timescale and improbable fortune. 4.5 billion years of relentless geological and atmospheric transformation, of volcanic eruptions spewing gases that would form early atmospheres, of cataclysmic asteroid impacts delivering water and organic compounds, of the slow, grinding dance of plate tectonics recycling crust and regulating climate, and crucially, of the emergence of life itself, which gradually, painstakingly, transformed a poisonous early atmosphere into the oxygen-rich air we breathe today. This was not intelligent design in the conventional sense, but a breathtakingly complex interplay of chance and necessity, an incomprehensible stroke of luck played out over deep geological time. To imagine we can replicate this miracle on a world like Mars within the span of a few human generations is to underestimate the profound challenges involved. Mars, the red planet, is not a blank canvas patiently awaiting human artistry. It is a world that actively resists habitation. Its current state is a cautionary tale of planetary evolution. Once, perhaps, a warmer, wetter world with a thicker atmosphere and a protective magnetic field, Mars lost these life-sustaining attributes. Its smaller size allowed its internal heat to dissipate more quickly than Earth's, causing its core to cool and solidify. This led to the demise of its global magnetic field, leaving its atmosphere vulnerable to being stripped away by the relentless solar wind over billions of years. What remains is a thin, tenuous shroud, less than 1% the pressure of Earth's atmosphere, offering little protection from solar and cosmic radiation and incapable of trapping enough heat to keep the surface from freezing. The Martian surface is a desolate, cold desert. Its average temperature hovers around a frigid -80 degrees Fahrenheit, though it can plummet to -225 degrees in winter at the poles. Its atmosphere is predominantly carbon dioxide, unbreathable to humans. Its water, while present, is largely locked up as ice in the polar caps and underground permafrost, or has escaped into space. The soil, or regolith, is permeated with toxic perchlorates, chemicals that would need to be removed or neutralized before any large-scale agriculture could be attempted. And then there are the dust storms, colossal events that can engulf the entire planet for months, choking solar panels, abrading equipment, and posing a severe hazard to any surface operations. Every single day on Mars, for every human inhabitant, would necessitate a continuous, complex, and failure-intolerant technological intervention just to maintain the basic necessities of life: breathable air, liquid water, adequate warmth, and protection from radiation. If one could somehow stand on the Martian surface without a spacesuit, the experience would be horrifyingly brief. The low atmospheric pressure would cause the fluids in your body, the moisture on your tongue, in your eyes, in your lungs, and even your blood itself, to begin to boil at body temperatures in about 90 seconds. Your final conscious moments would be an excruciating agony as your body literally vaporized from the inside out. The universe's verdict on unprotected human life on Mars would be swift, unequivocal, and brutal. You do not belong here. Beyond the specific challenges of Mars, the very act of journeying into space is a testament to cosmic tyranny, a battle against fundamental physics. To escape Earth's substantial gravity requires accelerating a spacecraft to a velocity of approximately 11.2 kilometers per second, or about 25,000 miles per hour. The energy required to achieve this is immense. Consider the Saturn V rocket, the marvel of engineering that carried humans to the moon. It stood 363 feet tall and weighed 6.2 million pounds at liftoff. The vast majority of this mass was fuel, expended with ferocious intensity in mere minutes, all to deliver a tiny lunar module weighing just 32,399 pounds to the moon, along with the command and service module. The inefficiency is staggering, akin to building an entire ocean liner to transport a single small suitcase across the Atlantic. And this monumental effort was merely to reach our closest celestial neighbor. The distances beyond the moon become nearly incomprehensible, stretching the limits of our intuition. Mars, at its closest orbital approach to Earth, still lies an average of about 34 million miles away, though this can extend to over 250 million miles depending on orbital positions. Even with our most advanced current propulsion technologies, a one-way journey to Mars takes 6 to 9 months. During this transit, astronauts are confined to relatively small spacecraft, exposed to cosmic radiation and living in microgravity with all its attendant physiological challenges. Now consider the stars, the nearest star system to our Sun. Alpha Centauri is approximately 4.37 light-years distant. A light-year, the distance light travels in 1 year, is about 5.88 trillion miles. So, Alpha Centauri is over 25 trillion miles away. Our fastest outbound spacecraft, such as the Voyager probes, are traveling at speeds that, while impressive by terrestrial standards, are utterly dwarfed by interstellar distances. It would take Voyager 1 approximately 73,000 years to reach the vicinity of Alpha Centauri, assuming it were even heading in that direction, which it is not. 73,000 years, multiple generations, thousands of them, would live and die in transit, never knowing Earth, their planet of origin, nor their final destination, existing solely as links in a vast, unimaginably long chain of cosmic migration. The psychological and societal implications of such multi-generational voyages are profound and largely unexplored. This tyranny of distance and energy is mathematically enshrined in the Tsiolkovsky rocket equation, a fundamental principle of astronautics. It dictates that the change in velocity a rocket can achieve is directly proportional to its exhaust velocity and the natural logarithm of the ratio of its initial mass to its final mass. In simpler terms, to go faster or to carry more payload, you need exponentially more fuel. But more fuel means more mass, which in turn requires even more fuel to accelerate at that additional mass. This creates a vicious cycle, a mathematical reality that severely constrains our cosmic ambitions with current chemical rocket technology. It means that building spacecraft capable of rapid interstellar travel, or even rapid interplanetary travel with substantial payloads, faces enormous, perhaps insurmountable, hurdles with conventional propulsion. Thus, the dream of creating new Earths, of seeding humanity across the cosmos, is not merely an engineering challenge waiting to be solved with sufficient ingenuity and willpower. It is a confrontation with the fundamental scale of the universe, with the immutable laws of physics, and with the billions of years of unique evolutionary history that have made our own world habitable. The universe does not readily yield to our desires. It presents a series of obstacles so profound that they force us to question the very feasibility of our grandest cosmic aspirations, pushing the boundaries of what is possible and what may forever remain in the realm of dreams. The red dust of Mars and the distant, cold light of the stars serve as constant reminders of this immense, almost impossible challenge. The human element body, mind, and spirit in the void. Our very consciousness, that ephemeral yet profound phenomenon that allows us to gaze at the stars and contemplate our place among them, to formulate these grand dreams of cosmic expansion, is itself a product of exquisite biological fragility. It exists because of the precise and delicate arrangement of approximately 86 billion neurons in our brains, interconnected by trillions of synapses, all operating within a tightly controlled biochemical environment. This remarkable organ, comprising only about 2% of our body weight, consumes a disproportionate 20% of our body's oxygen and glucose, maintained at an exact temperature and pH balance. Disrupt this delicate equilibrium for mere minutes through lack of oxygen, a significant change in temperature, or a chemical imbalance, and the intricate dance of neural activity falters, higher cognitive functions cease, and the light of consciousness, as we experience it, dims and then extinguishes. This same hypersensitive consciousness, so dependent on terrestrial stability, is what we propose to send into environments that actively seek to undermine its very foundations. The long-term physiological decay experienced in space is relentless, a slow-motion dismantling of our Earth-evolved bodies, beyond the immediate challenges of bone demineralization, muscle atrophy, fluid shifts, and radiation exposure. There are more subtle, cumulative effects that we are only beginning to understand. The immune system appears to be dysregulated in space, with some functions suppressed and others overactive, potentially increasing vulnerability to infections or autoimmune responses. The microbiome, the complex ecosystem of trillions of bacteria, viruses, and fungi that live in and on our bodies and play crucial roles in digestion, immunity, and even mental health, is likely altered by the confined, sterile environments of spacecraft, the specialized diet, and the physiological stresses of spaceflight. The long-term consequences of these microbial shifts are largely unknown. cognitive function itself may be impacted by long-duration space travel. While the heroic image of the sharp-focused astronaut persists, studies have hinted at potential subtle declines in certain cognitive domains, possibly due to a combination of factors including radiation effects on the brain, chronic stress, sleep disruption, altered cerebral blood flow, and the monotonous, confined environment. The very structure of the brain can change, with evidence of fluid shifts within the skull and alterations in white and gray matter observed in astronauts after extended missions. However, the assault on the human element is not solely physical. The psychological toll of long-duration space missions, particularly for future colonists who may face lifetimes of isolation and confinement, is a profound concern. Humans are social creatures, evolved in open spaces, under blue skies, surrounded by the rich sensory tapestry of a living, breathing planet, the scent of rain, the feel of wind, the sounds of nature, the vibrant colors of a forest or a sunset. What happens to the human psyche when confined for years or even generations within the sterile, metallic corridors of a spacecraft or a Martian habitat, where every square foot is meticulously engineered and maintained at tremendous cost, where there are no natural horizons, no unpredictable weather, no spontaneous displays of natural beauty beyond the porthole view of a distant Earth or an alien landscape? Studies of individuals in isolated and confined environments on Earth, Antarctic research stations, submarine crews, long-term prisoners, reveal a spectrum of psychological challenges: depression, anxiety, irritability, interpersonal conflicts, sleep disturbances, and cognitive decline, often referred to as the third quarter phenomenon, where morale dips significantly partway through a long mission. These terrestrial analogs, however, occur under Earth's familiar gravity, with the knowledge that the natural world, friends, and family are ultimately reachable. For space colonists on Mars, millions of miles from Earth, the isolation would be far more profound, the confinement more absolute, and the possibility of return, if it exists at all, would be a distant and complex undertaking. The psychological weight of knowing that your survival and that of your community depends entirely on the flawless functioning of complex human-made technology, with no natural safety net, would be immense and unrelenting. Yet, amidst these challenges, there is also the potential for profound, even transformative, human experiences. Many astronauts who have viewed Earth from orbit or the Moon have reported a cognitive shift in awareness known as the overview effect. Seeing our planet as a fragile, luminous blue marble, suspended in the vast darkness of space, with no visible borders or divisions, often instills a deep sense of the interconnectedness of all life, a profound appreciation for Earth's beauty and preciousness, and a renewed commitment to its stewardship. It is an experience that can transcend intellectual understanding, becoming a deeply emotional and spiritual realization. Could this perspective, writ large across a future spacefaring civilization, foster a greater sense of global unity and responsibility? But as we contemplate adapting to survive in these alien realms, we inevitably encounter deep ethical questions about adapting humanity itself. If the unyielding harshness of space demands more than our current biology can withstand, do we turn to genetic engineering to enhance radiation resistance, to modify our metabolism for different atmospheric compositions, or to reshape our physiology for different gravity wells? If we design artificial organs that function more efficiently in microgravity, or neural interfaces to augment cognitive function or mitigate psychological stress? At what point do these modifications begin to alter what it means to be human? Is such a transformation the ultimate expression of our adaptability, our ingenuity, our drive to survive and transcend limitations? Or is it a betrayal of our evolutionary heritage, a departure from the very nature that defines us, who decides what constitutes an acceptable alteration, and what are the potential unforeseen consequences of tinkering with the complex. Interconnected systems of human biology that have been refined over millions of years. The children born on Mars or in orbital habitats would know no other reality. Earth, for them, would be a story, a legend, a distant blue point of light in their sky. Their senses would be attuned to the engineered environment, their bodies perhaps subtly different, shaped by reduced gravity and a different sensory input. Would they feel a connection to Earth? Or would their primary loyalty be to their new off-world home? Would they still consider themselves human in the same way terrestrial humans do? Or would they represent the first generation of a new, post-Earth branch of humanity? The first true aliens of our own lineage. These are not merely speculative flights of fancy. They are fundamental questions that will confront us if we seriously pursue the dream of becoming a multi-planet species. The human element, in all its complexity, body, mind, and spirit, is both our greatest asset and our most vulnerable component in the quest to live beyond Earth. The void challenges not just our technology, but our very identity, forcing us to ask what we are willing to become in order to survive among the stars. The unseen universe and its silent questions. The cosmic stage upon which we aspire to enact our grand dramas of exploration and colonization is itself a realm of profound mystery, far stranger and more enigmatic than our everyday intuitions can readily grasp. Our comfortable narratives about the universe's origins and structure often mask deep uncertainties and unsettling paradoxes. Consider the Big Bang, that common shorthand for the universe's genesis. The term itself, coined somewhat derisively, conjures an image of a colossal explosion occurring at a single point in a pre-existing void. But the reality, as understood by modern cosmology, is far more nuanced and mind-bending. There was no sound, for there was no medium to carry it. More fundamentally, the Big Bang did not happen at a specific location in space. Rather, it happened everywhere, simultaneously. It was an expansion of space itself, not an explosion in space. In the earliest moments, the entire observable universe, with all its nascent matter and energy, was compressed into an unimaginably hot, dense state. Space itself was unfurling, like an infinite flower blooming from an infinitesimal seed. If the universe has no edge, as current observations suggest, then asking where the Big Bang occurred is akin to asking where on the surface of an expanding balloon its inflation began. The expansion is happening at every point on the surface. This understanding, however, leads to its own set of puzzles. One of the most significant is the horizon problem. When we look at the cosmic microwave background radiation, the faint afterglow of the Big Bang, an omnipresent whisper of microwaves filling all of space, we observe an astonishing uniformity in its temperature across the entire sky. Regions of the CMB that are on opposite sides of our observable universe, so far apart that light, traveling since the dawn of time, could not possibly have crossed the distance between them, nonetheless share almost precisely the same temperature, down to tiny fractions of a degree. How could these causally disconnected regions have reached thermal equilibrium if they never had a chance to interact, to exchange heat? It's like finding 2 cups of coffee, brewed in separate, sealed rooms miles apart, having cooled to exactly the same temperature without any communication. To resolve this and other cosmological conundrums, the theory of cosmic inflation was proposed. This theory posits that in the first fleeting fraction of a second after the Big Bang, a period almost unimaginably short, perhaps from 10 to the power of minus 36 seconds to 10 to the power of minus 32 seconds, the universe underwent a period of exponential superluminal expansion. It didn't break the cosmic speed limit by having matter travel faster than light through space, but rather by stretching the very fabric of space-time itself at an accelerated rate. During this inflationary epoch, a region smaller than a proton could have expanded to the size of a grapefruit almost instantaneously. This rapid stretching would have smoothed out any initial temperature variations, explaining the uniformity of the CMB, and also flattened the geometry of space to the near-perfect flatness we observe today. But inflation, while solving some problems, introduces new questions and even more astonishing possibilities. What triggered inflation? What caused it to stop so precisely, allowing for the more leisurely expansion that followed, which permitted stars and galaxies to form? And if inflation happened once, could it be a continuous process, happening in other regions of a much larger reality beyond our observable horizon? This leads to the concept of eternal inflation and the multiverse hypothesis, the idea that our entire observable universe might be just one bubble or pocket universe among an infinite or vastly numerous ensemble of other universes, each potentially born from its own inflationary event, and each perhaps with its own unique set of physical laws, fundamental constants, and even dimensionality. If this is true, then what we call the immutable laws of nature might be mere local ordinances, provincial rules that apply only within our specific cosmic neighborhood. Imagine the implications for future interstellar explorers. Reaching the edge of our bubble could mean encountering a boundary where our physics gives way to something utterly alien, rendering our technology useless and our very biology incoherent. The strangeness of the cosmic stage extends to its most fundamental constituents. We believe we understand matter, the solid stuff of tables, chairs, planets, and our own bodies. But delve into the quantum realm, and this familiar solidity dissolves. Atoms, once thought to be indivisible building blocks, were revealed to be mostly empty space. A hydrogen atom, for instance, is about 99.999996% void. If its nucleus were the size of a pea, its electron would orbit roughly a kilometer away. You, solid as you seem, are predominantly empty space, a fleeting configuration of quantum fields, a ghost made of mathematical patterns held together by forces we can describe with incredible precision, but whose ultimate nature remains elusive. And these fundamental forces, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, present their own cosmic puzzle. Why these four forces? Why do they possess their specific, measured strengths? The universe appears to be exquisitely fine-tuned for complexity and the emergence of life. If you were to alter the gravitational constant by even a tiny fraction, stars either could not form or would burn out too quickly. Adjust the strength of the strong nuclear force slightly, and the elements necessary for life, like carbon, could not be synthesized in stellar furnaces, or atomic nuclei would be unstable. Tweak the electromagnetic force, and the very chemistry upon which life depends would break down. This apparent fine-tuning is often referred to as the anthropic principle, the observation that the universe's fundamental constants and initial conditions seem to be precisely those required for conscious observers like ourselves to exist and observe it. Does this imply cosmic luck of an extraordinary degree? Are we living in a specially selected universe from a vast multiverse ensemble where most other bubble universes remain sterile and lifeless because their physical constants are not conducive to complexity? Or is there some deeper, yet undiscovered, physical principle at work that necessitates these specific values? The cosmic inventory grows curiouser still when we consider the dominant components of the universe: dark matter and dark energy. All the ordinary matter we can see and interact with, the stars, galaxies, planets, and ourselves, accounts for only about 5% of the total mass energy content of the universe. Approximately 27% is attributed to dark matter, an invisible substance that does not emit, absorb, or reflect light, interacting with ordinary matter only through gravity. Its presence is inferred from its gravitational effects on the rotation of galaxies and the bending of light from distant objects. Dark matter forms the invisible scaffolding around which galaxies coalesce and cosmic structures form, yet we do not know what it is made of. The remaining 68% of the universe is even more mysterious: dark energy. This is a hypothetical form of energy that permeates all of space and appears to be driving the accelerating expansion of the universe, pushing galaxies apart at an ever-increasing rate. Its nature is one of the biggest unsolved mysteries in physics. Think about that nearly 95% of our universe consists of substances and energies we cannot directly see, cannot touch, and barely understand. We are like explorers in the 16th century trying to map the globe with only 5% of its surface visible, navigating by the subtle effects of invisible currents and unknown landmasses. And it is into this vast, largely unknown ocean that we dream of launching our fragile colonial vessels. Amidst this cosmic grandeur and profound mystery, one observation stands out with unsettling clarity: the Great Silence. Our Milky Way galaxy alone contains an estimated 100 to 400 billion stars. Many, if not most, of these stars are likely to host planetary systems. Current estimates suggest there could be tens of billions of potentially habitable, Earth-sized planets in our galaxy. Given the age of the universe and the billions of years that many of these planets have existed under relatively stable conditions, it seems statistically probable that life should have arisen elsewhere, and that at least some of that life should have evolved intelligence and developed technological civilizations. Even if the emergence of such civilizations is exceedingly rare, say 1 in a billion suitable planets, there should still be thousands, if not tens of thousands, of spacefaring civilizations in our galaxy alone. Some of these would likely be far older and more advanced than our own. Yet, when we scan the skies with our radio telescopes, when we look for signs of astroengineering or interstellar travel, we find nothing. No unambiguous signals, no Dyson spheres, no evidence of galactic colonization. The galaxy appears hauntingly empty of the technological signatures we might expect. This is the Fermi paradox. Where is everybody? The silence is profound and deeply unsettling. Does it mean that life itself is incredibly rare, or that the transition to intelligence is a major bottleneck? Perhaps technological civilizations invariably self-destruct before they can achieve interstellar travel. Or maybe the challenges of living beyond one's home planet, the very challenges we are contemplating, are so immense that they represent an insurmountable great filter that silences countless emerging civilizations before they can announce their presence to the cosmos. Or a more solitary thought: perhaps we are truly among the first, or even the only, technological species to emerge in our galactic neighborhood. The unseen universe, with its hidden constituents, its mind-bending origins, and its deafening silence, poses not just scientific questions, but deep existential ones, casting a long shadow of uncertainty over humanity's ambitious dreams of cosmic expansion. The indifferent stage in humanity's uncertain future. The universe, for all its breathtaking beauty and intricate laws, operates with a profound and chilling indifference to the aspirations, struggles, and very existence of conscious beings like ourselves. There is no inherent morality woven into the fabric of space-time, no cosmic justice ensuring the triumph of good over evil, and certainly no special concern for the survival or extinction of Homo sapiens. Stars explode as supernovae, sterilizing any nearby planetary systems with lethal radiation, not out of malice, but because their core chemistry dictates it. Asteroids and comets, remnants from the solar system's formation, drift through space on gravitational tides, occasionally impacting planets and potentially ending billions of years of evolutionary progress in a geological instant, as one likely did for the dinosaurs. Gamma-ray bursts, the most powerful explosion in the universe, can erupt from distant galaxies, sending focused beams of high-energy radiation across intergalactic space, capable of stripping atmospheres and causing mass extinctions on any unprotected worlds in their path. These are not targeted assaults, they are merely the impersonal workings of cosmic mechanics. In this indifferent cosmos, any human presence beyond Earth would exist solely because we, through immense effort and continuous technological intervention, create and meticulously maintain the conditions for it. There is no natural, welcoming niche for humans anywhere but Earth. Every off-world habitat, every lunar base, every Martian colony, every generation starship would be a fragile, artificial island of habitability in a vast, encompassing ocean of lethality. Survival would depend entirely on the flawless, perpetual functioning of life support systems, radiation shielding, atmospheric containment, and resource recycling. This creates a fundamental contradiction at the heart of the space colonization dream we seek to expand human presence into a cosmos that is inherently hostile to that presence. We attempt to create persistence in an environment characterized by impermanence and entropy. We strive for safety and stability in a universe defined by cataclysmic violence and unpredictable danger. The challenge of replicating Earth's complex, self-regulating ecological systems, which took those 4.5 billion years to evolve their intricate web of interdependencies. Within the confines of an artificial habitat is perhaps the most daunting technological hurdle of all. Consider Earth's biosphere. It's not just a collection of organisms, but a dynamic system of interlocking cycles: the carbon cycle, the nitrogen cycle, the water cycle, the oxygen cycle, the rock cycle, all operating on planetary scales and over geological timescales to maintain a relatively stable environment conducive to complex life. The oxygen we breathe is not a permanent feature of our atmosphere. It is actively produced and maintained primarily by photosynthetic life, from rainforests to phytoplankton in the oceans. Without this continuous biological activity, atmospheric oxygen would gradually deplete as it reacted with minerals on the Earth's surface. To sustain human life in a closed habitat on Mars or in deep space, this entire planetary-scale life support machinery must be replicated, miniaturized, and managed with near-perfect efficiency and reliability. Every breath of air, every drop of water, every calorie of food, and every waste product must be meticulously accounted for, processed, recycled, and reintegrated into the system. The margin for error would be vanishingly small. A significant failure in the air revitalization system, the water reclamation process, or the food production units could lead to catastrophic consequences within hours or days. Earth's biosphere possesses enormous redundancy and resilience. If one ecosystem is damaged, others can often compensate. If one species goes extinct, others may evolve to fill its ecological niche. This robustness is the product of billions of years of evolutionary trial and error. Space habitats, by contrast, would likely be far less resilient, designed from first principles with a limited number of species and carefully engineered pathways, the most ambitious attempt to create a large-scale and materially closed ecological system on Earth. Biosphere 2 in Arizona during the early 1990s serves as a stark cautionary tale. Despite significant funding and scientific expertise, the 2-year experiment encountered numerous problems. Oxygen levels dropped to dangerously low concentrations. Many of the introduced pollinating insects died off. Most vertebrate species went extinct. Crop yields were insufficient to feed the 8 human inhabitants, and the crew themselves experienced interpersonal conflicts and factionalism. And this occurred on Earth, with access to external resources, sunlight unattenuated by vast distances, and the planet's natural gravity and magnetic field. Replicating such a system with even greater reliability, for indefinite periods, millions of miles from Earth, is a challenge of an entirely different magnitude. The perpetual reliance on fallible, human-made technology for every aspect of survival would create an immense and unceasing psychological burden for colonists. They would live with a constant awareness that their existence hangs by the thinnest of technological threads, that a critical system failure, a micrometeoroid puncture, or even a human error could spell swift annihilation. This is a stark contrast to life on Earth, where even if our technologies fail, the underlying environment generally remains habitable, offering a natural safety net. In space, there is no such fallback. Technological regression that might cause hardship or societal decline on Earth would mean certain extinction for an off-world colony. Furthermore, the tyranny of distance, as discussed earlier, would have profound long-term consequences for the human species if we were to successfully establish multiple isolated colonies. Communication delays measured in minutes, hours, or even years for interstellar settlements would make real-time interaction impossible. This would inevitably lead to cultural divergence. Different colonies, facing unique environmental challenges and developing under conditions of extreme isolation, would likely evolve distinct languages, social structures, values, and even mythologies. Over many generations, subjected to different gravitational fields, radiation levels, and perhaps even deliberate genetic modifications, biological divergence could also occur, potentially leading to the splintering of Homo sapiens into new distinct species, no longer able to interbreed or perhaps even to fully understand one another. Is this cosmic diaspora the grand destiny of intelligence, to diversify and fill every available niche? Or does it represent a tragic fragmentation, a loss of shared human identity? The universe, in its cosmic indifference, sets the stage but offers no script. It provides the raw materials, the elements forged in stars, but no guarantees of success or even survival. Is our relentless drive to expand beyond Earth, to push against these seemingly insurmountable obstacles, a testament to a uniquely human capacity for transcendence, an expression of our deepest exploratory instincts? Or is it a form of collective hubris, a refusal to accept our inherent biological limitations and our profound dependence on our home planet? Perhaps it is a mixture of both. The history of life on Earth is a history of adaptation, of overcoming environmental challenges, of radiating into new niches. The transition from aquatic to terrestrial life was an epochal leap, fraught with peril for the pioneering organisms. Is the transition from planetary to interplanetary, and eventually interstellar, existence simply the next great evolutionary hurdle? As we stand at this crossroads, a species capable of dreaming of the stars but not yet truly capable of inhabiting them sustainably, we must confront these deep contradictions. The impossible challenge of living beyond Earth forces us to question not just our technological prowess, but the very essence of what it means to be human. What values do we prioritize? What aspects of our terrestrial heritage are essential to carry forward into the void? And what might we need to leave behind? or transform in order to survive the long-term fate of Earth itself. And our Sun adds another layer to this existential calculus. Our planet will not remain habitable forever. In about 1 billion years, the gradually brightening Sun will likely make Earth too hot for complex life. In about 5 billion years, the Sun will exhaust its core hydrogen fuel and expand into a red giant, potentially engulfing the inner planets, including our own. On the longest of cosmic timescales, even the universe itself has a finite lifespan of productive activity, with star formation eventually ceasing and matter itself perhaps decaying into a cold, dark, empty expanse. Against this backdrop of ultimate cosmic transience, the drive to spread life and consciousness beyond our single, vulnerable world takes on a different, perhaps more urgent, meaning. If consciousness is a rare and precious phenomenon in the universe, then perhaps ensuring its long-term survival, beyond the lifespan of a single planet or star, is a moral imperative, a responsibility we owe not just to ourselves, but to the cosmos itself. The stars watch in silent indifference, their light traversing eons to reach our eyes. They have witnessed the rise and fall of countless worlds, countless possibilities. Our future among them remains unwritten, a narrative we are only just beginning to compose, fraught with peril, yet gleaming with the audacious hope that defines our species. The impossible challenge awaits, and with it, the potential for a transformation far more profound than simply changing our address in the cosmos. It is a challenge to redefine our place in the universe and, in doing so, to discover what humanity might yet become. The journey to the stars, as we have seen, is not a simple extension of our terrestrial adventures. It is a confrontation with the deepest truths of our existence, our profound biological connection to Earth, the staggering scale and indifference of the cosmos, and the inherent fragility of life and consciousness. The universe presents us with a fundamental paradox. It is the crucible that forged us, yet it is also an environment that actively seeks to unmake us the moment we step beyond our planetary cradle. Every law of physics, every biological imperative, every psychological reality seems to underscore the immense, perhaps insurmountable, difficulty of truly making a home beyond Earth. Yet, in the face of these overwhelming challenges, humanity continues to dream, to design, to reach outward. Is this mere folly, a species-level hubris refusing to acknowledge its limits? Or is it something more profound, an intrinsic characteristic of consciousness itself, to question, to explore, to strive to transcend its apparent boundaries? Perhaps our destiny is not to find easy answers or comfortable new homes, but to engage with these impossible questions, to push against the very fabric of what seems possible. In doing so, we learn more about the universe, but more importantly, we learn more about ourselves. The silence of the cosmos, the vast distances, the lethal environments, these are not just obstacles, they are mirrors reflecting our own vulnerabilities, our courage, our ingenuity, and our deepest fears. The attempt to live beyond Earth, whether it ultimately succeeds on a grand scale or remains a series of heroic but limited forays, will inevitably change us. It forces us to consider what aspects of humanity are truly essential, what we must carry with us to the stars, and what we might be willing to transform or even sacrifice. The stars will continue their silent vigil, indifferent to our triumphs or failures. Earth will continue its cosmic journey, a tiny oasis of life in an ocean of desolation. But the questions raised by our celestial ambitions will linger in the human spirit. What is our purpose in this vast, unfeeling universe? Are we merely a fleeting biological accident on a minor planet? Or are we the means by which the cosmos becomes aware of itself, a conduit for consciousness to spread, and perhaps, in some distant future, to comprehend the totality of its own existence? The path ahead is shrouded in uncertainty. There are no guarantees. But the human story has always been one of facing the unknown, of stepping into the darkness armed with little more than curiosity, determination, and the audacious hope that beyond the horizon lies something worth discovering. The impossible challenge of living beyond Earth may be the ultimate expression of this enduring human spirit, a testament to our refusal to simply accept the world as it is, and our unyielding desire to imagine and strive for what it might yet become. The cosmos waits. And we, children of Earth, stand at the edge, looking out,